Okay, 9.2, estimating a population mean. So remember, the goal of statistical inference is to use information obtained from a sample and generalize the results to the population being studied. As with estimating the population proportion, the first step is to obtain a point estimate of the parameter. A point estimate is the value of a statistic that estimates the value of a parameter. So the sample mean is going to be our point estimate for our population mean mu. Okay, we had p hat for our point estimate in 9.1. All right, example, computing a point estimate. Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represents the weights in grams of 17 randomly selected pennies minted after 1982. So treat the data as a simple random sample and estimate the population mean weight of pennies minted after 1982. So if we're finding the mean, right, all we're going to do is add all those up and divide by 17 because there's 17 of them. 2.46 plus 2.47 plus 2.49 plus 2.48. I'm just putting these values in my calculator. And finally, plus 2.45 divided by 17 so that we get our point estimate is, I need a pen. Our point estimate is 2.64. No, I'm sorry, 2.464. 2.464. Now, remember to round statistics to one more decimal point than the raw data. So because we had 2 decimal points in the raw data, I left 3 here. But proportions we're always going to round to 3 decimal places, right? Okay, so in that example, a different random sample of 17 pennies would likely result in a different point estimate of the mean, right? So for this reason, we're going to construct confidence intervals for the population mean just like we did for the population proportion. Okay, so before, our population proportion was basically this for our confidence interval. This time, it's just going to be this, right? Instead of p hat, our point estimate is x bar. So, a confidence interval for the population mean is of this form, just like the confidence interval for the population proportion. Now, remember that the distribution of x bar is approximately normal if the population from which the sample is drawn is normal or the sample size is sufficiently large. So let's remember what that means for our sample size to be approximately normal is greater than or equal to 30, right? Okay, in addition, the distribution of x bar has the same parent population, so mu sub x bar is going to equal mu, just like mu sub p hat equaled mu. And a standard deviation is going to be represented by S over the square root of n. Okay, sigma sub p hat, remember, was the square root of p times 1 minus p over n. Okay, this right here is actually going to present a little bit of problem because we have to use S, and there's additional variability introduced by using S in place of sigma. Okay, so that's why we have this student's t distribution. And the reason it's called student's t distribution is the guy that discovered it, came up with it. He published his work under a pseudonym. He didn't use his real name, and so he just called himself a student. Okay, so suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, okay, then the distribution of t is from this formula, okay? And this is the student's t distribution with n minus 1 degrees of freedom, where, of course, x bar is the sample mean, and S is the sample standard deviation. Now, to help understand degrees of freedom, let's think about this. Suppose you have 5 pens of different colors, and 5 friends, want to borrow a pen. Your first 4 friends have some freedom as to which color they choose, right? But that last person has no freedom. He's just got to take that only colored pen that's left. So there's n minus 1 degrees of freedom because that last one doesn't have freedom of choice. Does that make sense? All right, now, this interpretation of t is exactly the same as that of a z-score, except, of course, we're going to use the t table instead of the standard normal table. And the t statistic represents the number of sample standard errors x bar is from the population mean. Okay, same thing we did last time, except we're using a different chart. All right, so let's look at this. If we obtain 1,000 simple random samples of size 5 from a normal population where the mean is 50 and the standard deviation is 10, then it says determine the sample mean and sample standard deviation for each of the samples. Okay, so they've done this here with the z-scores and the t-scores, and then computed a histogram of each. So notice that the histogram for Z, this one right here, is symmetric and bell-shaped. Okay, it's centered at 0, and virtually all the rectangles lie between -3 and 3. Okay, so this is -10, so here's -5, right? Here's +5. So basically they lie between 3 and -3. Okay, in other words, that means it follows a normal distribution, right? That's what it means to be normal. But look at this histogram with the t values, okay? It's also symmetric and bell-shaped and centered about 0, but look how long the tails are. They go past 10 and past -10, okay? So that means your data is more dispersed. It's way more spread out. So it's unlikely that this follows a standard normal distribution. It turns out that the shape of the t distribution depends on the sample size. Okay? So there's different t distributions for different sample sizes. The spread in the distribution of the t decreases as the sample size n increases. That should make sense. In fact, it can be shown that as the sample size n increases, the distribution of t behaves more and more like a standard normal distribution. Okay? So let's look at the properties of the t distribution. It's different for different degrees of freedom. It's centered at 0 and symmetric about 0. The area under the curve is equal to 1, of course. Okay, and so the area to the right of 0 equals 1/2 as the area to the left of 0 because it's symmetric. As t increases or decreases without bound, the graph approaches but never equals 0. In other words, right, what that means, what that's saying is, okay, here's it increasing without bound, decreasing without bound. So it gets closer and closer and closer to 0 without ever touching it, just like everything else we've talked about. The area in the tails of the t distribution is a little greater than the area in the tails of the standard normal. Because we're using S as an estimate of sigma, and that makes more variability. Okay, S samples are varying also. Okay, as the sample size increases, the density curve of t gets closer to the standard normal density curve. Okay, this result occurs because as the sample size increases, the values of S get closer and closer to the values of sigma, there by our law of large numbers again. All right, so here is a t distribution for a sample size of n equals 5, n equals 15, and the standard normal. So the blue one, they're saying, is the standard normal curve. Okay, notice the orange, it's kind of hard, they chose poor colors here for a distinction, but the orange one is n is 5, so that's the one on top down here, right, and lower. And with n equals 15, the red one, look, it got much closer to the normal distribution. As n gets larger, it gets closer and closer to a normal distribution. Okay, now recall that the notation z sub alpha, remember, is used to represent the z-score whose area under the normal curve to the right of z sub alpha is alpha, right? So on the z-scores, our chart is giving us this area. Okay, well, similarly, we've got t sub alpha, but it gives us the area to the right. Okay, the area to the right. So the shape of the t distribution depends on the sample size. Therefore, the value of t sub alpha depends not only on alpha, but the degrees of freedom, n minus 1. So you've got a table in your Canvas classroom, in your course documents module, same place you had your normal distribution table, okay, for a t distribution. And the far left corner, let me go ahead and go to, I think on the next one is a piece of that. So this far left column, labeled DF, that stands for degrees of freedom, right? And it's already in n minus 1 format. And then the top row across here represents the area under the t distribution to the right of some t values. So find the t value such that the area under the t distribution to the right of the t value, so once again, it's this, and we're looking for this area, is 0.2, assuming 10 degrees of freedom. That is, find t sub 0.2 with 10 degrees of freedom. So here's my degrees of freedom. Oh, look, it's right on that dark spot, and I'm going to go over to where 0.2, because this is automatically to the right. So be careful whether you're using your Z chart or T chart. Okay, and I'll see that that intersection is 0.879. Okay, now if the degrees of freedom that we need is not listed in the table, look down here towards the end. It starts going, I think it's after 30. Let me look on mine. No, it's after 40, right? You have one all the way down to 40, but then after 40, it goes 50, 60, 70, 80, 90, 100, 1,000. So if the exact degree of freedom we're interested in isn't looking, for example, if we needed 43 degrees of freedom, round, so we would use 40. If we needed 47 degrees of freedom, we would use 50. Okay. Also, if we have degrees of freedom more than 1,000, notice this last row says Z. That comes from the normal distribution table. Okay, so anything when n is more than 1,000, no matter how much more, we're just going to use this last row. Okay, we're now ready to construct a confidence interval for a population mean. So, sample data come from a simple random sample or randomized experiment. Sample size is small relative to the population size. We still need our sample size to be less than or equal to 5% of the population size. And the data come from a population that is normally distributed or the sample size is large. Then, right, same conditions as before. Then our confidence interval for mu is given by this. Notice it's basically the same thing we did last time. Remember last time we had, let's see, p hat plus or minus z sub alpha over 2 square root of n 1 p 1 minus p over n. Okay, it's just we have a different formula, but the same thing, point estimate and margin of error. Okay, where t sub alpha over 2 is the critical value with n minus 1 degrees of freedom. Now, because this confidence interval uses the t distribution, it's a lot of times referred to as the t interval. So if you see that, it means, oh, a confidence interval using t. So the margin of error is this right here. Right, here's our margin of error. So we have a formula for that now. Okay. Notice that a confidence interval about mu can be computed for non-normal populations, even though the student's t distribution requires a normal population. Right? The confidence interval is accurate despite minor departures from normality. If a data set has outliers, the confidence interval is not accurate because remember, the sample mean or the sample standard deviation x bar or s, neither one of those are resistant to outliers. Remember way back when we talked about resistance? So before we use this idea of, our t intervals, sample data should always be inspected for serious departures from normality and for outliers. Okay, but that's easily done with histograms and box plots. All right, so we got new formulas. Let's look at an example. Construct a 99% confidence interval about the population mean weight in grams of pennies minute after 1982. Okay, so the first thing I need to do, earlier we just found that mean, and now though it's asking us to construct a confidence interval, right? So first I need to verify that these data are obtained randomly, and they're telling us that it is, they did earlier. And the sample size is small relative to the population. Well, we have 17 things, and pennies minted after 1982, that's way less than 5% of pennies minted, right? Okay, so because it's small relative to the population, we now need to draw a histogram to determine if it's normally distributed. So remember our method for drawing a histogram. I need a frequency distribution first. So this is the weight in pennies and the frequency. Let's see. Okay, it's all 2.4 something. So how about doing, okay, gonna have to make that a little bit bigger. 2.43 to 2.45. So that would be 2.46. Remember, they got to be the same size. So 3, 4, 5. That means 3. So I need 6, 7, 8. Then I need Then I need 9, 10, 11. So basically that is 2.49 to 2.51. Okay. 6, 7. I'm just looking at what I'm doing. It's all 2.4, so I'm just looking at that last number if you're wondering what I'm doing. Right? 9, 8, 5, 0, 4, 6, 5, 9, 7, 5, 6, 5, 6, 7, 4, and 5. Okay, 5, 10, 13, so 15, 16, 17. Okay. All right, so if I were going to draw a histogram, and my frequencies need to go up to 8. So 2, 4, 6, 8. Okay, my first box from 2.43, 2.45, 2.48, 2.51. So 43 to 45 go up to 6. Need to make that a little wider. And then 8. And then 3. Okay. So, okay, approximately normal, right? It's not heavily skewed right or left, right? Okay. So then let's construct a box plot to make sure there's not any outliers. All right. I need my 5-number summary for that. So let's put these in order. I had a 1, 2, 3, 4 of those. 1, 2, 3. Not quite going to fit on here. Nearly 2.48. I'm going to just do it over here. 2.48. 2 4 9s. And so and a 2.5. Okay. So my minimum value is 2.44. Okay. My median, my max is 2.50. Medium. There's 17 data points. So 17 plus 1 is 18. The ninth one, 1, 2, 3, 4, 5, 6, 7, 8, ninth one. That's my median. Okay. So now 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Let's see if that's right. 1, 2, 3, 4. Okay, so 2.45 is my first quartile. And 1, 2, 3, 4. And my second quartile is at 2.485. So if I'm drawing a box plot, okay, I need to figure out my fences. I'm going to do that in a different color just because we're getting jammed up here. So my interquartile range is 2.485, 2.485 minus 2.45. All right, so to find my fences, right, I've got quartile 1, 2.45 minus 1.5 times my IQR, 0.035. I really don't need to draw it. I just need to know where the outliers in particular. Okay, and then it's 2.485 plus 1.5 times 0.035. All right, so let's see what we get. 2.45 minus 1.5 times 0.035. This is 2.3975. Okay. Okay, no outliers in that direction. 2.485 plus 1.5 times 0.035. 2.5375. Largest value, no outliers in that direction. Okay? So if we don't know that our sample is normal, this is our first step. Draw the histogram and make sure it's basically normally distributed and make sure there's no outliers. You can't have skewed data. You can't have outliers. Okay, if your sample size is small, less than 30, right? Okay, so we verified that. Now we're going to do the sample mean. Oh, we had that sample mean earlier. Did I write it down? Let me look and see. I think I wrote it down over here. Oh, maybe it's in my calculator. Please get my calculator. Was it 2.464? That was the sample mean, wasn't it? Yeah, 2.464. Okay, and we need the sample standard deviation, which requires that chart. Actually, I'm going to do that on the calculator, right? So go into our list. Okay, so all right, now I'm gonna, after list one, I've gotta clear it out, and I'm gonna enter all this data. But definitely, if I have more than 5 or 6 data points, definitely want to use my calculator for that standard deviation. And 2.45 finally. Okay. And it tells us, let's see, yeah, and for the X bar we got 2.464. And for S, we have 0.017. Alrighty. Okay, now we want a 99% confidence interval. So that means alpha is 1 minus 0.99, which is 0.01. All right. Our sample size was 17. Okay, so that means we have 16 degrees of freedom, and alpha over 2 is 0.005, right? 0.01 divided by 2. Okay, so now let's look on our table. Let's think about what this is that we want. It's really probably important to draw this and figure out what we're talking about. Okay, so if we're looking on our table, we want a 99% confidence interval. So we want this to be 0.99, right? Which means this over here is 0.005, and this over here is 0.005, so that the entire thing equals 100%. Okay, so this is what the table's going to give me. This is what I'm looking for. So I'm looking across the column that says 16 for my degrees of freedom until I come to 0.005. And that intersection is at 2.921. Okay, so 2.921. This is T sub alpha over 2 is 2.921. Okay, so now we're just going to plug into that formula that we had, which the formula, right, is X bar plus or minus T sub alpha over 2 times S over the square root of N. All right, so X bar, so we have 2.464 plus 2.921 times 0.017 over the square root of 17. And then we have it minus. Right? It's just plugging into that formula. Let's see what we get. Okay, 2.921. So I got, here's my interval, 2.476. Now I can do a second enter and just change the minus. Oh, I should have done the minus first. 2.452 to 2.476. Okay, that's my confidence interval. Okay, I'm 99% confident that the mean weight of the pennies, minute after 1982, is 2.452 grams to 2.476 grams. Now remember, confidence refers to the confidence in the method. If we obtained 100 samples of size 17 from the population of pennies minute after 1982, we would expect about 95 of the samples to contain an interval that includes the actual mean. Now, here, we can't be confident that this interval is one of the 95% because 5% of them do not contain it, right? But 95% of them will contain the actual mean. Okay, so hopefully that was similar enough to what we just did that made sense. Now, what should we do if the requirements to compute a t-interval are not met, right? For in other words, if there are outliers or it's not normally distributed, right? Well, we could increase the sample size to beyond 30 observations, or we could use non-parametric methods. Okay, non-parametric methods don't typically require normality, but non-parametric procedures are not going to be presented in this course. Yay, right? I heard everybody. Woohoo! Okay. Okay, but so our sample size, determining what sample size we need for this course. Okay, the sample size required to estimate the population mean with a level of confidence of whatever we need with a specified margin of error is given with this formula. And remember, just like last time, n is rounded up, not just rounded or rounded off, rounded up. Okay, so here's an example. Back to the pennies. How large a sample would be required to estimate the mean weight of a penny manufactured after 1982 with 0.005 grams, within 0.005 grams with 99% confidence? I'm just going to plug into the formula. All right, just going to plug in to the formula. So the sample size we would need is, now be careful. This is z sub alpha over 2. We've gone back to the z chart. So let's think about what that means in order to be able to read this, right? We want a 99% confidence interval. So 0.99. Okay, that means the rest of it's got to be 0.1. So this is 0.005. And this is 0.005. Okay, and the Z table gives us to the left, right? It gives us the area to the left. All right, so I've got a couple of choices. Okay, I can either find this number and then this one and subtract it. Remember when we did that? Remember we said, okay, I could find this area and then I could find this area and subtract them. Or because these things are symmetric, right? Think about this. This is symmetric. Okay. I could find this area. Well, I could find this area, right? This area right here. And then just make it negative. Does that make sense? Or this method, whichever you prefer. All right, so I'm looking on my normal distribution table now, and I'm looking in the body for 0.005. 0.005, and let me see where I'm at. 0.005. Okay, I've got a 0.0051, so I've got a 0.0051 and a 0.0049. This coincides to 2.57 and this to 2.58. Because this is exactly halfway, right, to 0.005, I'm going to go halfway in between here. So my Z sub alpha over 2 is negative 2.575. Okay, because I used the symmetry. Okay. And then times S, it tells us is 0.02. And the margin of error that we want is 0.005. So let's plug that in our calculator. Let's see. I'm looking for my typo in here because I do not believe that 10 is the appropriate number. So let me see what I've done wrong here. 2. Oh, I didn't square it. Yeah. All right. So 106.09 and because we round up, I would need N to be 107 if I did not meet those requirements of it being shaped without being skewed right or left and no outliers. Okay? Okay. So find the t value such that the area to the, now we're back to t's, such that the area to the right of the tail is within 0.05 is 0.05 with 10 degrees of freedom. Well, right of the tail, that's exactly what this is telling me, right? So this is 0.05. So I can just look and read my chart exactly. So 10 degrees of freedom is right here, and 0.05. Oh, passed it. So 1.812. Okay. Find the area, find the t-value such that the area left of the t-value is 0.01 with 18 degrees of freedom. All right, so I know I'm going to be looking right there, 18 degrees of freedom. But this time it says that the left is 0.01. Okay, so I want to use that idea again of symmetry. All right, so 0.01 over here, because it's symmetric, is what I'm really going to look at, but then I'm going to use the negative value. Okay, so I'm looking at 0.18 degrees of freedom and 0.01 right here. 18 degrees of freedom. 2.552, but that's really this value, what the chart is telling me, but from symmetry, I know it's negative 2.552. Okay, now it asks me to find critical t-values. Notice these are critical values when we're talking about our confidence intervals that correspond to a 90% confidence interval. All right, so what that means is this needs to be 0.90, which means this is 0.5 and this is 0.5. Right? Okay, and this time we're doing 20 degrees of freedom. Okay, so I'm going to look across until I have, where's my, oh, y'all watch me, y'all watch me. This is a 0.05, right, because one, okay, and so 1 minus 0.90 is 0.1 divided in half is 0.5. So 90%, that leaves 10% on the edges, so 5%, 0.05. So here's my, oh, same one, except I'm just going down to 20 degrees of freedom. So 1.725. Okay? Okay. Determine the point estimate of the population mean and the margin of error for the confidence interval with a lower bound of 20 and an upper bound of 30. Well, think about this. The point estimate should be in the middle of your confidence interval. So if your confidence interval bounds are between 20 to 30, then your point estimate would have been 25, right? And this one's easy to see what's halfway in between there, but if you had two numbers, remember, and you want to find halfway in between them, add them together, divide by 2. Okay, now the margin of error, remember your margin of error is this. So if I'm looking for my margin of error, I know that I can do either one. I can take my point estimate and I can subtract my margin of error, and that's going to leave me my lower bound. Or I could have said, well, my point estimate plus my margin of error is going to give me my upper bound. I can solve either one of those. Either one of those is going to tell me that my margin of error is 5. Right? Okay. Okay. A simple random sample of size n is drawn. The sample mean is found to be 18.4 and the sample standard deviation is found to be 4.5. All right, so we've done this a couple of times by hand and by the chart. Let's do it on our calculator now. Okay, and again, the instructions, from your book are under the technology tips from the text. But here's what we're going to do. Okay, so we're going to go into our stat, go over to tests, and then if you scroll all the way down, you'll see number 8, or you can just hit the number 8 and it'll bring it up. But notice number 8 is called T-interval. All right, and then you've got data or stats. Go over and highlight stats. Let me go back in there. Messed up stat. Tests. Okay, T-interval. So when I'm over into stats, I'm going to go down and I'm going to enter my sample mean, 18.4. And then standard deviation sample, and you'll notice this is what's in the list, S sub x, is 4.5. Okay, the sample size comes next, so that's 35. And then your confidence level, and this says we want a 95% confidence level, so that's 0.95. You then go down to calculate and hit enter. And it will bring up 16.85 to 19.95. Okay, now the great thing about that is if I'm asked a different question with something slightly different, I can just hit second enter. Sorry, I can't on this. And then I'm just going to go back into stats, over to tests, number 8. But the only thing I have to go down and change is that n, and let's change it to 50 because this time it said construct a 95% confidence interval for mu if the sample size is 50. Okay. Everything else stays the same. And I get 17.12 and 19.68. Okay. And it asks, how does the margin of error, no, it asks, how does increasing the sample size affect the margin of error? Well, let's do our margin of error for n equals 35 and n equals 50. Remember, we had this formula. Our margin of error is T sub alpha over 2 times S over the square root of n. So, if I do it for 35, I'll do it up here. My margin of error, right? T sub alpha over 2. Okay, we want 95%. So that means we got let me get my chart. 34 degrees of freedom. 0.025. 2.032. Times 4.5 over 35. And then the same thing down here. The only difference is going to be times square root of 50. So let's put that in our calculator. 2.032 1.55, and then if I just do second enter and change the 35 to a 50, I get 1.29. So it decreased, right? Our margin of error got smaller. Okay. Construct a 99% confidence interval from U if the sample size is 35. All right, so let's go back into our stat, over to our test, and this time everything's the same. We're taking the sample size back to 35, but we're changing our confidence to 0.99. And we get 16.33 to 20.48. Now it asks the same thing. So it asks the same thing about how our margin of error is affected. So this time, our T sub alpha, since we want a 99% confidence level, so we're looking with 34 degrees of freedom, and I want to go over to, yeah, if you need to draw this, draw this. So 0.005 with 34 degrees of freedom, 2.728. We're back to 35. All right. 2.728. And we got 2.08. So this time it increased. Okay? So if your sample size gets larger, your margin of error decreases. If your level of confidence gets larger, your margin of error increases. Okay, what about this? If the sample size is 15, what conditions must be satisfied to compute the confidence interval? Well, basically, it's got to be approximately normally distributed. All right, so you make sure that your sample size is less than 5% of the population size. You make sure that the shape of it is normal, not skewed right, not skewed left, and that there are no outliers. Okay, the data represent the length in miles of a random sample of tornadoes from a specific area. The variable length represents the number of miles a particular tornado was on the ground. Draw a relative frequency histogram of the variable length using a lower class limit of 0 and a class width of 4. Okay, so we've got, what do we have, length and frequency. Okay, 0. Now think about this, 0, 1, 2, 3. That means we're going 0 to 3 for our class width to be 4. 4 needs to be right here, right? 4 minus 0. So 4, 5, 6, 7, 8, 9, 10, 11. What do we got? We got all the way up to 22. All right, 12 to 15, 16 to 19, and 20 to 23. All right, so 0 to 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 4 to 7. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 to 11. 1, 2, 12 to 15. 1, 2, 16 to 19. And then 2 left. All right, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 36, 32, 4, 6, right? That's a nice way to check ourselves. All right, so our histograms got to go up to 22. Okay, so maybe 5, 10, 15, 20. Okay. So 3. Because I'm going to do 0 here, I'm going to do the others. So 4, 8, 12, 16, 20, 24. Okay, 0 to 3, 22. 4 to 7, 8. 8 to 11, 2. And then 2. And then nothing, and then 2. Comment on the shape. Skewed right. Right? Not normal. Skewed right. However, look, we got 36 records. 36 samples. So we're good. But still, if I didn't have 36 samples and I did this distribution, nope. Okay, draw a box plot of the length. Are there any outliers? Now, once again, I'm going to let my calculator do this time. We already physically did one while ago to refresh our memory on that. Let's let our calculator do it. So to refresh our memory on that, let's go back into, we need to go back and enter this data now. I've got to clear that other data. From list 1, and I'm just going to enter all this data. Okay, so you can do it along with me. Be careful, I just caught myself entering 10.2 instead of 1.02. 1.02. Okay, and I did have 36 by the time I got to the end. So I feel confident, hopefully, about that. All right, so once I get them entered, now I'm going to hit my second y equals from up at the top, my graphing keys. I'm really going into that stat plot, right? Going into stat plot and going down to plot 1, make sure everything's off except plot 1. And I'm going to turn it on and choose that first box plot one. Notice also you could do the histogram in here, right? This one told me to do it with specific intervals, so I really couldn't do it in here. But I want to choose that first one, so it's going to show me my box plot. Okay, after I go down to everything else, I'm going to go into my zoom and scroll down. I think it's number 9, which is zoom stat. So go into zoom stat, and there it is. Now, if I needed to draw this out and have my scale and everything, which I'm going to do down here, hit trace. And notice what happens when you hit trace. Your cursor goes up and it tells you that the minimum is 0.11. So, sorry, I need a pen. All right, so 0.11 is where my minimum is. I'm going to do a number line. Let me scroll over way over to and see what that's at. Oh yeah, I'm at 22 something. So I'm going to start at 0. 5, 10, 15, 20, 25. All right. Then at 0.695 is already my first quartile. My median's at 2.0. Third quartile is 5.95. So there's my box. And this is a whisker. And then at 13.34, that's the end of this whisker. But at 14.3, I have an outlier. At 20.83, I have another one. And at 22.43, I have another one. Right? From tracing, I can get my values and how to draw that box plot. Okay, explain why a large sample is necessary to construct a confidence interval. Okay, because of outliers and skewed data, right? Then you have to have a large sample size to make it approximately normal. Okay, now it says construct and interpret a 95% confidence interval for the mean length of a tornado in this area. All right, so and we've already got all that entered in our list 1. So let's go back and find our mean for that from the stat calc 1 variable statistics, and I can get that my mean is 4.41, and there's 2 up there, so 4.414. Okay, and my standard deviation is 5.546. So we're now going to stats, test, into interval. Oh, it already had it in there because, duh. Sorry, guys. I could have went right into the interval because I said that right before I did this. I already had all my information in list 1. All right, but I have to go down and change my confidence interval to 0.95. Okay, and calculate. So I get 2.54 to 6.29. Okay, that finishes up 9.2. 9.3, the last section in chapter 9, is just a putting it all together section, and so there's no information in there. It's just more examples, really. So if you're still a little shaky or uncomfortable, not real comfortable, then you could watch that before you go do your homework on 9.2, because all that is just more practice, not any new content. Okay, let me know if you have any questions.